Okay, so now we know a couple of things about nuclear chemistry reactions. One, we know how to balance those equations, right? We always have to balance the mass and we have to balance the charge. The second thing that we know is we have a general sense of how to always have these reactions go toward more stable products, right? We look at the belts of stability and we try to figure out the ratio of neutrons to protons, or if the mass of the nucleus or the number of protons in the nucleus is greater than 83, we worry about alpha decay, excuse me. So alpha decay, if it's greater than 83, beta decay, either beta minus or beta plus if it's less than 83, right? So we know something about what these reactions are, and we know how to balance these equations. One of the things about nuclear reactions, is that they're really not equilibrium processes, right? It's not something where you get a certain amount of the decay product and a certain amount of the starting material, and then we can calculate a KEQ for these reactions, right? Which is what we've done for a lot of these things. The delta G, the KEQ, the E cell, all these are concerned with equilibrium of these reactions. Nuclear reactions are kind of one-way streets. Once you lose that alpha particle, it's not coming back to add back into that nucleus and undo the alpha decay that has happened. And so when we talk about these reactions and we think about like how are these reactions proceeding, we're not going to think about things like free energy. We're not going to think about things like reduction potential. We're not going to think about things like KEQ. Instead, we're only going to be concerned with how fast do these reactions go. So what is the rate of these reactions? And we're going to have some formulas and equations, of course, to figure this out. Now, these equations are going to be things that you have already seen and we've already used. And so we can kind of just modify them just a little bit to be concerned with the most important thing of nuclear reactions, which is the half-life of these processes. All right. So nuclear reactions in general are all first-order processes. Are first order. And so without looking, you can remember the integrated first order rate law. Whoops, that's not how you spell integrated. Okay, maybe you might need to look this one up. I did. But the integrated first order rate law is that the natural log of A, so at some point you have, well, the concentration of A, right? At some point you have A, right? And that point is at time t, and that's given by the rate constant times t plus the natural log of however much you started with of A. And furthermore, we can remember what the formula for half-life is. So I'm going to use T sub h, because when I use a 1/2 here, people always try to do math with it. So T sub h is our half-life. And the formula for the half-life of a first order reaction, basically what we do is we put in 0.5 times A0 for this value and solve this equation. And what we get is the natural log of 2 over K. Okay, so this is the half-life. And I think it's worth taking a moment to talk about what the half-life means. We talked about this briefly in previous chapters, but it's important to really kind of hammer down what this means. What the half-life means is this is how long a reaction must go to reduce starting material by 50%. So if you start with 1 gram of A naught, how long it takes to get to 1/2 gram of whatever your A compound is given by this half-life, right? And this half-life can be in seconds, minutes, years, months, days, whatever, right? As long as you keep it the same in these two equations. So the half-life is how long it goes to get to 50%. And so what we're going to do when we talk about this is we're going to really focus on how do we calculate the half-life, but also and what we're going to do is we're going to kind of try to eliminate K. We're not ever really going to know rate constants for these nuclear reactions, for these nuclear decay reactions, just because it's really hard to figure out. And it's really not that important of a number for us to figure out. If we know the half-life, we pretty much know K already. K is the half-life, half-life is K. We just have that natural log of 2 number in there, right, to kind of mix it up. So we're going to calculate half-lives, we're not going to calculate K. So we're going to rewrite these formulas in ways that allow us to not have to include the rate constant, K. So there's going to be three formulas that we're going to talk about, right? And it's all going to depend on what information you're given. So if you want to calculate the half-life and you're only given an initial amount, right, A0, and an amount at time t, and that's going to be A, and then of course t is your time, right? If you're given these three values, we want a formula that we can figure out what the half-life is from these three pieces of information. So of course, what you could do is plug all of this into this integrated first order rate law, solve for K, plug K into the half-life equation, and that would work, right, every time. Instead, what we can do is we can solve this half-life equation for K and then plug that in up here and then solve the whole thing for half-life. And what we get is we get the natural log of 2 times t divided by the natural log of the ratio of A0 to A. So this is a formula, and this is, you can argue whether or not this is a simpler formula, but it's only one formula as opposed to needing two formulas to figure this out. And so you can just plug these three numbers, if you're given those, into this equation and calculate your half-life from there. Now, other times you might be given the half-life. So what if you're given, this is our given, right? There we go. Right, what if you're given the half-life and a starting amount? Not half-time, half-life. And initial amount. And you want to know how much of this material is going to be left after time t. Well, the first thing you should do is take the time t divided by th, and that's going to give you a number, right? And we'll call that x. And this is the number of half-lives that have passed. Right? So every time a half-life passes, we reduce our amount by 50%. So you start with 100% of your material. After one half-life, you have 50%. After your next half-life, you have 25%. After the half-life after that, so after 3 half-lives, you have 12.5%. 4 half-lives, 6.25%. On and on. Forever, 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 right? So if we know the number of half-lives that have passed, we can use that number instead of dividing t by the half-life every time, right? And so I'm going to just plug that number in as x. Anytime you see x, you could just assume that that is the time t divided by the half-life. So if we want to calculate A for this value, A is going to be equal to 2 to the x power times A naught. And this just comes from, again, doing the same thing here, right? If we know what the half-life equals, right, and we know what time t equals, if we're solving for A, we can just plug this value, ln2 over the half-life, in for K up here and do some algebraic manipulations, and we get this. So the amount that we have left after a certain amount of time is equal to 2 raised to the number of half-lives times the initial amount, right? So the number of half-lives is given by T over TH. And then we can reverse this formula also and find out the initial amount if we know how much of our stuff we have left, right? If we know how many half-lives have occurred, right, and we know how much material we have at a certain amount of time, we can tell how much we started with, right? So if you're given A instead of A naught, you can also solve these. So these are the three main equations that we're going to use to calculate things related to the half-life of nuclear reactions. But we're going to talk about the half-life pretty much exclusively in the worksheets and stuff. And so these equations, again, you don't necessarily need to memorize these equations because all of these come from these two ideas, the integrated first order rate law. It's just that when we do nuclear equations, we're going to use these types of things a lot. And so we just kind of write out the formulas and use them that way. Okay, that does it. That's all the information that you need for the nuclear chemistry unit in this course. And that is the last unit of this course. So congratulations, you've made it to the end. It's amazing. So do the worksheets on the nuclear chemistry stuff. If you have questions or concerns about that, make sure you can balance equations, do beta decay, alpha decay, know what those terms mean. Make sure that you can do the calculations with the first order rate laws and the half-life and all that kind of stuff. There's a worksheet for that as well. And if you're having trouble with any of that, please let me know so that we can go over it and talk about that kind of stuff. But there's not going to be any more video lectures from me unless there's a huge demand for something, which I doubt. So this is it. You have made it through the end of the course. So give yourself a pat on the back. Well done.